So we're starting off with static electricity, and it's really important even though it's really fundamental. It is something that elementary students play. Actually, it's something that my son plays with. I do have some static electricity toys at home, a mini Van de Graaff that he plays with, which is pretty neat, and hopefully we get to do that in class as well. So we have three different ways today to kind of talk about how things get charged up. So hopefully we could play around with it and I can explain it through these diagrams I'm going to have. So here we go. So first one that we did, and pretty much how we always start off, is charging by rubbing. Okay, normally what you have is you have some sort of plastic pipe. It could be glass as well. The properties will be a little bit different if it is glass. And you have another object. In our class, most likely I asked you to grab something really fuzzy. So let's just say you have a piece of cloth here, whether it's a jacket, a towel, whatever, a small hand towel. Both of these objects are going to have positive and negative charges. So remember, let me get the good color, they have protons and electrons. I'm not going to draw a whole bunch because we have billions of molecules here. We're going to draw a significant amount that we can show a good amount of charge, but at the same time not be so tedious. I usually like going around 5, but it is up to you. So 5 protons there. 1, 2, 3, 4, 5. 5 protons there. Initially we want them to be neutral, so I'm going to have electrons added to it, and it doesn't really have to have an order. I just put it on top, but you can have randomly, but you want them next to the protons. So it will make more sense later, but for now we want them next to the thing. Now for both of these objects, they're going to be non-metallic. So they are insulators. Because they're insulators, these electrons aren't free to move, meaning that unlike a metal, the electrons in the metal are free to move anywhere on that thing. They share, they kind of flow around. That's how electricity works. Because these electrons are bound to that nucleus, or that atom, even if you put a bunch of electrons on one side, it's not going to travel through the other side. So that's what an insulator is. And this only works, charging by red, only works with non-metallic. Works best with plastics, glass, things like that. So we have two objects that are very, very different. In this case, we have glass and something that's very furry or fuzzy. And what we're going to do is I asked you to rub them together. So when you're rubbing them together, I probably should have done this better. So when you're rubbing them together, what's going to happen is, let's say here's the pipe, here's the cloth, and you're moving it back and forth really, really fast. You're going to create friction, and then you're going to create heat, and then what's going to happen is technically electrons get excited. Because of the heat, they get more energy, so that means they have motion, more motion in them, and they're willing to do more stuff because you're giving them energy to do things. What normally happens, and there's no way to predict this, is that the electrons are going to be transferred. So you have electrons getting excited here, electrons getting excited here, and electrons from one object is going to transfer into the other object. Where it goes, you don't know. You have things to test which one becomes negative, which one becomes positive, but it is something that you can't predict. So normally the best explanation I have for you is that as electrons get excited, they're going to go into the object that has the lower valence electron orbit, or it's going to be more happy. So whether you're filling up a valence electron or a valence orbit, or it has one extra one it's going to give off, or it just has equal amounts but one is lower in electron shell, it's going to go to that one. That's the best explanation for it. Can we predict it? No, but is it consistent? And the answer is yes. So even though we don't know where it's going to go, it's going to be the same every time. So after we rub it, this is what's going to happen. So let me get my picture. So here's my pipe. Here is my cloth. So this is after rubbing. And what's going to change is only electrons. Protons stay the same, and it has to. If you change protons, what's going to happen is, remember, protons determine what the material is. So if you change the number of protons, technically, if you pull them off, it's kind of a nuclear reaction. I mean, that's what's happening in a nuclear reaction. You're pulling off neutrons and protons, and it causes a great explosion. So we're not doing that. We're only pulling electrons. So it's going to go from one object to another. When I'm asking you to do something like this, I will usually tell you where it's going, or you decide yourself. So after rubbing, one's going to gain a charge. You decide, or I'll tell you where to go. For this case, let's say the pipe gains electrons. So when that happens, we're going to draw original one. 1, 2, 3, 4, 5. And let's just say it gains 3. 1, 2, 3. Okay. In real life, it's gaining tons and tons of electrons, but we're just doing a representation of drawing it. So if this one gains 3, that means 3 of these have to come from here. So they have to equal. So what you started with here, 5 protons, still the same. 5 electrons, 5 electrons. So that's a total of 10. We still end up with 10. We're not gaining or losing electrons total, but we're just transferring it. Okay, so this is charging by rubbing. So you are rubbing something which is creating friction, increases heat and movement, and the electrons are going to rest or jump into the object that has the least amount. Now, this is happening on insulators. Okay, so that means that it's not moving around. Even if you're holding this, let's say this is your hand. Your hand is right here, holding onto this object right here. The electrons will stay on because remember, as an insulator, they can't move off. So that's a really cool thing. Could you do this with metals? Yes, kind of. But you have to be very careful how you do it with metals, because if you are grounding it, which we'll talk about once we get into metals, it's going to suck out the electrons. So it'll make more sense once I do a video about, or once you see the video about metals.